Hi, I'm David Tao and you're watching the Theories of Everything program. This is the third part of our series Foundations of Knowledge, and in this program we'll be looking at the nature and artefacts of reality. In the first part of this series we examined the nature of truth and the evolution towards a method of verifying truth. We understood that in early species there was a neural reward system, which of course still exists today, and from that evolved a process of trial and error to verify the world around, to determine what would best suit survival of the species. From the trial and error process right through early civilization, right through to early civilization in fact, evolved around the 17th century the process known as the scientific method, which was a formalised, more abstract process of the verification of truth in relation to the environment that humans lived in. So this was a major threshold. Prior to that, knowledge had been gleaned in a rather haphazard way, because that's the only way it could have been accumulated. Humans wondered, hypothesised and tested the world around them. They looked at the sky, saw the stars, finally worked out that the position of the stars, position of the planets signified the seasons. So they were able to take advantage of that knowledge. They also were able to take advantage of information regarding positions of the stars to travel around the world, to travel across the oceans using the stars as a guide. So they put together a giant jigsaw. They wondered about the nature of reality then. They started off with the supposition that everything was composed of earth, fire, water, air. But as time went on, in fact it wasn't really until the beginning of the 20th century, in fact, that it was realised that, generally accepted, that matter was composed of atoms. Earlier Greeks and many others had hypothesised that the nature of reality was atomic, but again it hadn't been formalised or proved in any rigorous manner until the beginning of the 20th century. And in the last century, particularly a little over the last century, possibly from about the last 150 years, we had major theories emerging covering theories of heat in the form of the theory of thermodynamics, theories of light in the form of electromagnetism, Maxwell's theory of electromagnetism, much more formalised theories stemming from Newton's 17th century when he developed an early unified theory of time and motion and force and gravity. That later evolved again in the early 20th century towards a more sophisticated theory by Einstein, a theory of gravity and a theory of motion, space and time. And then again early in the last century, evolved quantum theory, unified theory of the atomic nature of matter and the subatomic nature of matter. Now these are the major theories. These are that still evolve today. The early theories relating to the atomic nature of matter have evolved through to the Standard Model, and that has evolved through to various theories such as superstring theory to try to combine all the different bits and pieces relating to forces and matter, all the earlier theories. So we have the emergence of the super theories. But leaving aside those physical theories, there are many other areas of knowledge that began to evolve again, particularly over the last few centuries, and have started to culminate today. One might call a major one of these a unified theory of mind. And one of the first of these theories was proposed by Edelman with his neural group selection theory, which says basically that neural structures compete and categorise information that they see in the world around them, and that's how memories are formed. As neurons fade away, get strengthened through processes of learning, adaptation and memory. So we see that the theories of everything don't really encompass everything, because as well as theories, knowledge to do with the mind, there's biological knowledge as well. The knowledge of how life evolved, the knowledge of the blueprint of life, which we've discussed a number of times. And so theories of life, theories of mind are still evolving, and really there is no one encompassing theory of everything, and probably there never will be. We also saw in the previous program the tools that evolved to help shape our understanding of the foundations of knowledge. All these tools go way beyond the normal senses of humans. But as well as that, we've developed sophisticated systems of mathematics and logic, and tools such as the computer that can help us go to another level again in our understanding of foundations of knowledge. By the beginning of last century, things seemed to be going very well for the scientists and mathematicians. The structure of knowledge was gradually being filled in, and it looked very consistent, and there looked to be no major problems ahead. Unfortunately, around 1900, Bertrand Russell found a major flaw in what's known today as set theory, and it basically overturned some of the basic axiomatic theory of mathematics. There could be paradoxes and there could be inconsistencies, and that of course was a major problem for all mathematicians. Now this was made worse, or if you like a larger crack was discovered in 1931 when Gödel discovered that, or proposed that for any set of consistent axioms there were still some theorems that may not always be able to be proved or disproved. So with these two theorems of what were called undecidability, mathematics was on fairly shaky ground. Not totally shaky ground, because there were lots and lots of theorems and lots of sets of axioms that could be proved to be consistent and complete and verifiable. But there was lurking in the background this other possibility. And an equivalent level of uncertainty was raised about the foundations of knowledge by Alan Turing, around 1940, when he determined that a universal computer running a program, one would be unable to determine whether that program would ever stop, and that meant whether the particular problem running on the computer had a solution or didn't have a solution, was solvable or not. So we have two levels of undecidability. This was called Turing's halting problem. If you didn't know whether the program would stop, halt, or continue, then you wouldn't know whether the problem was solvable. A third layer of uncertainty was introduced, of course, in quantum theory, and by Heisenberg's principle. Heisenberg proved that for particles at the subatomic level, you couldn't know all the information about them simultaneously. You couldn't know both their position and their energy or momentum to any level of accuracy simultaneously. You could know one thing accurately and another property accurately, but not both together. So this was another problem, if you like, another degree of uncertainty. Scientists were starting to live with these levels of uncertainty, but there was a great deal of unease. And then in around 1960, in the 60s, Gregory Chaitin, a researcher at IBM, discovered and has continued to develop his theories of randomness and uncertainty in mathematics. He developed a particular object which he called omega, a mathematical object, and that suggests that it relates Turing's halting problem to a particular type of mathematical equation called the Diophantine equations. If the Diophantine equations had a solution, then Turing's halting problem had a solution. The trouble was that omega, or the digits that make up omega, just like the digits that make up pi, for example, are completely random. The digits that make up pi can be easily computed, but the digits that make up omega can be computed with difficulty by putting in parameters into the Diophantian equations, but you never know what those digits will be. And that basically says that you never know, even though the overall object omega gives a probability of a program having a solution or not, you never know for certain whether it will or not. In other words, it introduces a great degree of randomness into the whole basis of mathematics. So it appears that there may be islands of mathematics which are provable, groups of theorems which are provable, but much larger, a much larger cosmos of mathematics in which the theorems are unprovable. So viewers, what does all this uncertainty mean in the foundations of our knowledge? Well, firstly, it means that a theory of everything is probably going to recede further and further away. Not only do we have a large number of major theories concerning inanimate matter as well as life and mind that probably can't be bridged with one theory, but it means because we can't access all the information that's needed, because there are so many levels of uncertainty in the things we can prove, it means that having a coherent theory of everything in the universe is probably a mirage. On the other hand, as time goes by, we are learning more and more about the real nature of the universe. So that knowledge has got to be valuable, and in fact it is. But at the same time, we're overturning many of our solid, certain, intuitive notions of how things are. Perhaps we need to examine some of these solid, practical notions of how the world works. They've stood us in good stead up till now. We've built things. We've established a civilization. But that civilization will rapidly change. One of the things where intuition in fact will have to be reversed is in the nature, understanding the nature of objects. Now when we talk about you and I, or this coffee cup or this pen, we talk about an object. But of course, understanding, if I see you in a coffee bar, if I see you walking down the street, I don't really know you because I know nothing about your history. I'm only seeing you in one or several frozen frames of time. The real you is not just an instantaneous view or even a view over a small period of time, a view over hours. The real you, or the real coffee cup to a lesser extent, is a story. To understand your place in society, to understand the real you, we need to go back in time and look at the you as an object, or the coffee cup as a process, not as an object. Of course, we talk about the evolution of processes. We talk about the evolution of things over time. We talk about the evolution of society, the evolution of the planet, of life on the planet. However, that's the wrong way to look at it, because we're still making the object paramount. The object, again, is just a moment in that process. The reality is the process. To get a real understanding of someone's place in society, you need to look at not only all the events in their lives, but all the relationships between those moments, those events, and other events that were occurring at the time. We can get another view of this significance of looking at things as processes by looking out into the universe. What we're seeing are not objects, actually, not stars, not planets, not galaxies. The photons that are coming from those objects are momentary. They give us a fleeting glimpse at a particular point in time of that object, and often the object is far back in the history of the universe. So we're getting information, if you like, about the process that formed that object, that evolves that object, going back in time. we're getting a slice of history into the universe. Some objects are close, so we're seeing them very close to the present. Some objects are far away. So we're getting different time slices going right back. So the object is the mirage, and the process is the real thing. Of course, understanding things in terms of processes and the relations between them is a fairly novel thing in our society. These are abstract forms, abstract structures that we've only just begun to use in common everyday parlance. Processes, for example, and relationships between them. Not only are the word process is commonly used both at the social and physical level. We talk about a peace process. We talk about a learning process. It's not a procedure, it's not a series of fixed steps, but it's a general connection between causal events that will eventually lead to the outcome that we hope for. So there's a significant difference, therefore, between a process, a procedure, and an algorithm. An algorithm is also a set of steps that usually these days runs on a computer, but you wouldn't really call it a process because the process is a more encompassing, over-encompassing thing. We learn to improve processes. But at the physical level, this is going to be a very important distinction. This comes now into the theory of quantum cosmology, where processes and the relations and the dynamic relations between them and events that have occurred since the beginning of the universe are beginning to dominate the understanding of space-time. Another knowledge artefact which has become increasingly important over the last few decades is the notion of networks. Although the term may have been in the language, the term process and networks may have been in the language for a lot longer, it's only in the past few decades that the concept of the network has been abstracted and forms an important basis for a lot of current theories. Nodes connected by links between those nodes, and it can be in a physical form, it can be an electronic network such as the internet, or it can be in a biological form such as the network of cells, neural cells in our brain. But either way, the network is just about everything. In the brain, the pattern of connections between the neural cells creates the knowledge, creates the memory, creates the reasoning power. And it also forms a channel for information to flow, but the information is also part of the network itself. It's not separate. And the same goes for complex networks like the internet. If you take, and the internet today consists of probably at least 500 million sites or more, connected in various ways that seem to cluster together. And if you take, for example, a random site and try to get to another site from the information in that, you'll probably get there in 4 or 5 clicks. The same phenomenon that was tested in the 60s and became known as the 6th degree of separation phenomenon, when a letter was sent between 2 people but with no predetermined path. Each person would send it to another person that they knew, who would send it to another person that they knew, and eventually it arrived after 6 stops. So the theory of networks, or graph theory as it's called again, is very important, but it's also led to many breakthroughs in traffic systems, for example, the travelling salesman problem. A number of theories have been developed that enable a network to be traversed in the least amount of time, with the least effort, at the least cost. And these are very important, such theories, in improving the productivity and quality of communication networks such as the internet. But also, again, in the latest theories of space-time, quantum cosmology to be precise, which is trying to get down to a theory of physical everything, networks play a major role, because we have networks as processes do. We have networks of processes that channel information about events between observers. These are evolving networks, and they're not played out on a stage of space-time against a static stage such as Newton postulated in his early work on mechanics. He said there was a timeless ether, a timeless space and time in which everything was played out. In fact, the networks combining the processes, joining the processes, allowing the flows of information between events, appear to be space-time, appear to be what reality is created out of. With this theory, the particles themselves are networks within processes and events. It's a very non-intuitive type of concept, but it appears to be the case that space-time itself is made up of networks or channels, information flowing between different parts of the universe, information flowing from the beginning of the universe right through to the present time. When we again look out into the cosmos, that is information coming through about processes linked together in complex networks, which have now been named as holographic networks, and a major principle called the holographic principle, which says that space-time consists of networks of information, joining processes, joining events. Another major knowledge artefact is the concept of a system and the concept of models. You can think of systems as a combination of processes in networks, relations between those processes. You can think of them as having an architecture, for example, and the concept of a system now is widely used, but it wasn't widely used 100 years ago. This connectedness of things that may not be physically connected, but have relationships between them to make up, for example, an education system, a social system, the weather system, many disparate parts, ecological systems, such as Gaia, for example. Systems have very interesting properties, and they allow us to model phenomena, again, to enable our knowledge to progress. See, what we have here is an abstraction process, an abstraction of structures of knowledge such as processes and networks and systems. This allows us to take an overview of physical reality, if you like. The fact that we cannot pin certain things down, we can't pin down the veracity of theorems, we can't get at all the information, means we have to apply these more abstract concepts, more abstract structures, allows us to go deeper. Systems are very interesting because they can be, they are dynamic, they're adaptive, they can be open or closed to the environment, they can be chaotic or deterministic, and they give us enormous insights into the physical processes going and the social processes going on around us. And we model them these days on computers. We take another level of abstraction. We abstract the variables, the parameters, the relationships between them, and we run those through a computer to try to get predictive outcomes, to try to judge whether the model, whether the system that we're working on is useful and that we can depend on it in the future. It appears, in fact, that as science discovers more about the universe, the real nature of reality continues to recede. And the more we realise that first impressions and first perceptions will change as time goes by. This concludes our three-part series on Foundations of Knowledge. I'm David Tao, and you've been watching the Theories of Everything program. I'll look forward to seeing you again next week.